We're going to start our talk on derivatives with kind of refreshing some things that we've talked about before. So some of this should sound familiar. So the first thing to recognize is that in the whole scope of math, the reason why calculus was created or discovered or uncovered is because Descartes had the question of wanting to find the slope of the line tangent to the curve. He said that it was super important. He in fact said it was the only thing he ever wanted to learn. And that's the one who died. So that's Descartes. Okay. The other guys died too, but that's the story. And the reason why he saw that it was so important is that if you go back to the Spudnator that we did, okay, remember when we watched that thing? If you, let me flip this, maybe that can help. Okay. What he said was, he says this is crazy, but you have a parabola, okay, that marks the height of an object, okay, height of an object, and say in like feet, and then the axis down here is time, maybe in seconds, okay, and I suppose just to make this a little bit more practical, I'm going to shift this up so we're not underground. And this is what he said. This was crazy. He said, if the blue graph, the parabola, represents the height of the object at any given moment, he said the slope of the line tangent tells you the velocity of the object at any given moment. That's what he said. And people are like, well, where'd you come up with that? That's kind of crazy. He said, no, stop and think about it. He said slope of a line. Okay? Slope of a line is rise over run. So if I take this object, this is like the stuff we were launching out in the common or in the courtyard, and he said, okay, let me just pause it like right here. This is kind of in mid-flight, right? He said this. The blue one is the height of the object at any given time. The tangent line is the velocity. And he said, here's why. Look at rise over run. You take this and you look at the rise over run at that point. Okay? Rise over run for this line right here. Well, what do I got here? I got feet that I'm going up here, and I've got my run is seconds. So my slope, which we define as rise over run, or change in y over change in x, is the units are feet per second. And it was a major breakthrough. It changed the world. Now the problem became, how do you find that slope of that line tangent? And so he died, he never could figure out, but what happened was that Newton came along and he says, I got it. He says, let's get really close to that point, because he says you can't find a slope of a line if you only have one point. That's the whole problem. So that's where he came up with that thing that said, well, wait a second, why don't we take a secondary point like this along with this point, and the distance between them, we'll call that delta x. And we'll find the slope of that line, and we'll let delta x get closer and closer to 0. But he said this, we can't let it actually equal 0, we'll let it get really super close to 0. And so he created this thing called the limit, which we just spent the last 3 weeks learning. And so he said, here's the deal. He says, if we can do that, then we have the slope of a line tangent, and he came up with this. He said, I got to think of something here, okay? We'll say the slope at any point, okay, any x value, is going to be equal to the limit as delta x approaches 0. Then you needed the slope of the line. And this is where we came up with that f of x plus delta x minus f of x over delta x. This is the formula for the slope of the line tangent to the curve at any given x value. Given some, I have to have some function, okay, whatever, and then I have to have some x value. And then if I do that, I can find that slope. Okay, that's the big picture, and that's kind of, this should sound familiar, right? We've talked about this a couple of times. Okay, now, what he did was then, he cranked this out for problem after problem after problem and finding different functions and different functions and different functions, and he found that the answer to the derivative is actually a new function that allows you to find the derivative at any given point. And so he says, I need to call that something. It's really a function that's derived from another formula, okay? And so that's where the definition of the derivative came from, because it's a function that's defined from another one. Okay? Now, what's really cool, and this is what we're going to take a look at right now, is if I want to graph the function, I'm going to start really easy. Okay? Here's my function. Now you got to look carefully here. The blue one's the function. See the 3? Okay. What is the slope of the line tangent to a horizontal line? It's actually the same as the slope of the line. Okay. So what's the slope of the line that's horizontal? 0. So watch. When I hit play, you see the green dot? The green dot is the slope at any given time. So what is the slope here? Well, the slope is 0. It always stays 0. I'm traveling left and right. On my function, I'm saying, what's the slope? Well, it's 0. Okay, well, that's a lot of fun. So if I put a different constant in there, like -2, if this is the equation, this is the line, y equals 2. What is the slope of the line tangent? Still 0. Okay? All right, so let's make it more fun. Let's type in a line y equals x. What's the slope of the line tangent? Can you see it? What's the slope? It's the same as the slope of the line. Okay? Those are the only two that are weird, because to be tangent, you kind of think it only has to hit one point. Here it hits a whole bunch of points. Okay? But watch this. So if I say 2x, what's the slope at every given point? It's 2. See how the green dot is showing you that it's 2. Okay? This is where it gets fun. X squared. Okay, where's my green dot? Where's my green dot? Where's my green dot? Oh, there it is. Oh, it was there for a flash. Okay, it's coming back. I'm gonna go through this slower. Okay, so look at this. Watch the green dot. The green dot is the slope. Right here, the slope is 0. See that? And this is the slope. The green dot is the slope of that line. See that? So no matter where I go, this is where if I put in that point 1, you can kind of see it maybe a little bit easier. Notice that the slope is negative when I'm to the left. Then it's 0, then the slope is positive. Just follow the green dot and look at the tangent line. Tangent line, look at that line. That line is negative, has a negative slope. Notice the green dot is below. Here, the green dot is positive, and it represents the slope. And we're doing it for every single possible dot. Okay, as we move along x. I wonder what would happen if we graphed, we drew all of the dots for the slope. Can you see what it kind of looks like? What does it look like? If you connected the dots for all the green ones, what would it look like? It would look like a line. In fact, it follows right on that line. Isn't that cool? So it follows that line. I wonder what the equation of that line is. Anybody know? What's the equation of that line? You can tell by looking at it here. It's got a very small slope. It's almost like you go up 0.2. Say it again. Y equals 1/2 x. Very close. It's 1/5 x. Okay, it's 0.2x. Slope is 0.2 of this thing. I wonder where that came from. All right, well, let's watch this. Change this to a cube. Okay. Watch your slope. Watch the slope. Here comes the dot. Watch the dot. What does it look like? Looks like a parabola. Hey, look at that. Is the slope of the line tangent ever negative? It's never negative. Okay, here we go. If you plotted every single slope for every single x value, it would turn into that parabola. In other words, I have a function, and then if the derivative is another function. The derivative is another function where it tells you what the slope is for every single point. It's pretty cool. Okay. Well, then we can get kind of fun. Okay. Okay, so watch the green dot. The green dot is the slope. Just I'll pause this at some point here. Okay. You see how the tangent line is positive, right? Its slope is this positive number here. Whatever this number is, maybe like about 3/4, 0.75. Okay. Any guesses? It's the cosine. Okay. That's funky. Okay. That means to find the slope of the line tangent to the cosine, or the sine, all you have to do is find the cosine. Okay? It's all about the dots. Now the question is, the first question, that's the first questions in your assignment, is there ever a function where you cannot draw a line tangent to it? At some point. Is there ever a function that it's impossible to find the slope of the line tangent at a point? At an asymptote? What kind of asymptote? Yeah, vertical or vertical. We got vertical, so we got slant. We got horizontal asymptotes. A vertical line. Okay, so x equals 3. Okay, what's the slope of the line tangent to that? It's a vertical line, it's undefined. So that is a case where you cannot find the slope of the line tangent. Okay? See, sometimes this would be something that you might want to just jot down. The slope of a line, of a vertical line, is undefined. Therefore, there is no derivative for a vertical line. You notice I'm not writing anything on the board? Okay, that's where it comes your job to say, ooh, that kind of sounds important. I should maybe jot that down. I should maybe like take a note in my notebook. Okay, so vertical lines, impossible. We can't find the. We can draw the slope, but we can't get an answer for it. There's no number for it. Any other functions that you can think of where it's impossible to find the slope? Like for example, like I said, if I do this. If I did this, we could find the slope everywhere we wanted to. No problem. Is there any time, where on a function can you not draw a slope? When the limit does not exist. Okay? So give me something where a limit does not exist. Can you do a piecewise function? I'm not going to do one right now. Give me another one. 1 over x. Okay? So, everybody, we just spent time talking about continuity, right? Continuous functions in that last one. Here is a case where the function is not continuous at x equals 0. Does it make sense that it's impossible to draw a line tangent when the function is not continuous? Okay, here's a place where it's not continuous. How can you draw a line tangent to that at x equals 0? You can't. There's no function. There's no point. Okay, so this is one where if I were to say to you, at what places, this is how the directions are asked in your assignment, at what places is the function differentiable? And it's really what intervals is the function differentiable? And so the first one is y equals 1 over x. That's that one right here. So where can we find the derivative? That's another way to say to find the derivative or to draw this or to find the slope. Well, for this one, every place from negative infinity to 0 and from 0 to infinity. Those are the places that are legal to find the slope, which means find the derivative. We can also say that's where it's differentiable.
So when you ask for differentiable, it wants
Where it can. It's based upon the question.
Okay.
In the textbook for yours, this is what we're looking at here. Are there any kind of functions where you can't find the derivative, like that one? But now one where it's not, it doesn't matter if it's continuous or not. I'll give you one. Okay. Absolute value function. Okay. So maybe I'll take off. I'm going to take off the graph here. The absolute value function is a continuous function. Okay? So that should mean, hey, if it's continuous, that should mean that we should be able to find the slope at any given point. But here's the problem. There is this really sharp turn right here. You can see that's where it bounces, you know. And the problem is you cannot find the slope of a line tangent to where you have this sharp turn. Okay? It's impossible. Because where would you put it? Okay? We don't know. It could be an infinite number of different slopes here. So if you ever have a function that has a sharp turn in it, you cannot find the slope at that point. You just can't. Okay? There's a special name for that, and that is, it's a cusp. So, a couple of things to state. Absolute value function also is differentiable on the same interval. So it's negative infinity to 0 and 0 to infinity. These are all of the legal places to find the derivative. But the reason for this one is because there is a cusp at x equals 0. A cusp is that really sharp turn. The reason that this one was differentiable all of here except for at x equals 0 is because this one was not continuous at x equals 0. Okay? So, if the function's not continuous at a specific value, bam, no derivative. If there's a cusp at the function at that value, there's no derivative. Can you think of another place where we can have that? Where we have a problem finding the derivative? Show you another example of each of those, and that is the greatest integer function. Okay, greatest integer function really is called a ceiling function. Okay, look at this. You see where there would be problems? So anytime you have, this is called a jump. Okay, anytime you have a jump, like a step function, that's another place where the function is not continuous. So y equals, and then the notation for that is this thing right here. Okay, that's how we say it. That's just to clarify it a little bit different than the absolute value. This one is differentiable from negative infinity to positive infinity, except for x cannot equal k, where k is in the set of integers. Meaning you can draw a slope at every given one of those points, except for at every integer. We're identifying when you can have a green dot. When can you have a green dot? Well, you can have a green dot at all these places except for where you have it's not continuous, where there's a cusp, where there's a jump, because that's where this one is. This one's called a jump. All right, I need to wrap up this with two statements, two rules. Rule number one. If a function is differentiable, oh, thank you. I was wondering what was going on there. If a function is differentiable at a point which means we can find the derivative, which means we can find a number for the slope, then the function is continuous at that point. If a function is differentiable, which means we can find the slope, the line tangent to the function, and give it a number, then for sure the function is continuous. The converse is not true, okay? If a function is continuous at a point, then it does not mean that the function must be continuous or must be differentiable at that point. If a function is continuous at a point, it does not mean that the function is differentiable at that point. Which one is the example of the ones that we did of that one? The absolute value. The absolute value function is continuous. It's not a place where you cannot find a value. Except the problem is you cannot find the derivative at the cusp. Make sense? So who's more powerful? Differentiability, which means being able to find the derivative, or continuity? Who has more power? Like if you know this, then you know something else. Differentiability. If you know that a function, if I tell you the derivative of a function at a certain value is something, you can say, oh, guess what? I also know that that function is continuous at that point, but not the other way around. All right. We will, you can go ahead and start your first assignment. It's a quick one. It's just about graphing. Because tomorrow, guess what I built?
Yes!
It's back in a new form. Yeah, it's the fun derivative calculator. First assignment, you should do that for tomorrow. It's a piece of cake.
No.
Yeah.
How is derivative spelled? Having one way on the board and another way on that poster.
Oh, it's an A.
It's an A?
I never noticed that.
I couldn't find the page in my notebook.
Derivative is spelt with an A.
Can we make it in cursive? Because big kids are